So in this question, we're going to be asked to linearize a nonlinear system and then carry out some state space analysis of it. So what's the system? Well, we've been given a nonlinear second order differential equation. So we've got d squared y dt squared equals 4 minus u squared divided by y squared, where y is going to be representing a displacement and u is going to be the control input. We're asked to choose suitable state variables, S1 and S2, and write down we'll write down this nonlinear second order equation in terms of two first order equations. So we can then basically write it in matrix format, and we'll then obviously going to linearize it at a later stage. So first of all, it's asking you to find the positive equilibrium position. So when is the system at rest? Under the condition that the input control is 1. Then it's asking us to linearize about this equilibrium position and evaluate, basically to do that, the Jacobian of the system, and then write down state space equations representing the linearized system at this equilibrium position. Then for this newly created linearized system, it wants us to calculate the eigenvalues and say something about the stability. And finally, what is the controllability and the observability of the system, assuming displacement y is the system output. So that's basically telling us what the C matrix looks like. So let's do this. We've got this nonlinear system, d squared y dt squared equals 4 minus u squared divided by y squared. We've got to choose two state variables. So looking at the d squared y dt squares, that tells us, well, we can't use anything of order 2. It's got to be order 1 and less. And we can see that y is obviously a contender, and also so will be dy dt. So we're going to choose first state variable as y and the second one as y dot, which is obviously y dot is dy dt. Because there's a relationship between those, we can see that S1 dot is going to be equal to S2, right? So if we differentiate y, we end up with y dot. And S2 dot is going to be d squared y dt squared. So that's going to equal 4 minus u squared divided by S1 squared. So if we put that in matrix form, that's quite easy. We've got two rows. So the first row is the first equation and the second row is the second equation. So we need to find the equilibrium point, and equilibrium basically means the system is stationary, and consequently its state derivatives are going to be 0. So what we have to find is the solution to the question of when is this system equal to 0, right? So when are the derivatives equal to 0? And we get two equations from that. The first one is obviously S2 equals 0, and we also get 4 minus u squared divided by S1 squared equals 0. And from the second equation, we can see, we can rearrange that, u squared equals 4s1 squared. So we can take this basically the solution when u equals 1, because that's what we've been asked to do. So basically we're saying that 1 equals 4 times S1 squared. So what does S1 got to be? So it's going to be half. So half times a half is a quarter. Multiplied by 4 is going to equal 1. So that will give us the first solution there. So given these two functions now, F1 equals S2 and F2 equals 4 minus u squared divided by S1 squared, we need to calculate the Jacobian matrix of the system, and we're going to have to later then evaluate this at equilibrium position. Right? So the Jacobian of this system, we've got two functions, so we're going to have two rows, and we've got two state variables. We've got S1 and then we've got S2. So the general form of the Jacobian, if we were talking about in terms of F1 and X, it would be the first term is F1 delta F1 delta X1, the second term at the top d F1 delta X2, and so on. In fact, that should be a 2 down there. That's wrong. So taking partial derivatives with respect to state variables, we need to calculate delta F1 S1. So we can see that there is no S1 S1 term in there, so that's going to be 0. If we differentiate this with respect to S2, that will end up going to a 1. We got it right here, we got the F2. So F2 is going to be the differential of this with respect to S1. So the first term is going to disappear, and we've got a 1 divided by S1 squared, so that's going to go to minus 2 times S1 cubed. So it gets rid of the sign there. And the third one then, there's no expression in here which is relating to S2, so the whole thing goes to 0. So we've got our 4 values, 0, 1, 2, u squared divided by S1 cubed, and 0. And then we have to substitute in the values. We substitute in the u equals 1, which we were told, and also the equilibrium position solution for S1, which was 0.5. So we stick those in, and hopefully we've got the right values, 0, 1, 2. So that's 1 divided by 0.5 times 0.5 times 0.5. So that's going to give us basically 16. We've also got to sort out the control, so we have to basically do the derivatives with respect to control variables as well, and that's then going to be, there's only one control, so there's a u, so we have to do df1 du and df2 du, okay? And again, we substitute in the values of u equals 1 and s1 equals 0.5. This then gives us the linearized equation around the control point at equilibrium, and as we can see, we've got x dot equals a x plus b u, right? So a is going to be this 1 0 1 16 0, and b is going to be 0 minus 8. Now we're then asked to look at the stability of the system, and we have to do that by looking at the eigenvalues of the system, which is going to be related to the A matrix. So basically we need to find, given J, we need to find the solution to the A matrix, which in this case we're calling the Jacobian, J minus lambda I, calculate the determinant, when does that go to 0? So again, we just have to substitute in the values. We put in our effective A matrix, minus lambda times I. We go through element by element, so this is 0 minus lambda, this is 1, this is 16, and this is 0 minus lambda. We solve that equation, calculate the determinant, which I'm representing now by these vertical lines. Here it's basically pointing out for you what it is. It's going to be this element times this element, take away this one times this one. So the characteristic equation is going to be lambda squared minus 16 equals 0. So we can see that then lambda squared equals 16. So what's the square root of 16? It's going to be 4. In fact, it's going to be plus and minus 4. Right? So we've got a lambda equals 4 and a lambda equals minus 4. So we've got one stable and one unstable eigenvalue. Therefore, we got this positive value as well in there. So therefore, the system is unstable. Right? Next thing to do is to look at our 2 by 2 matrix, and for what we've got for J, which is effectively the A matrix, and see whether or not the system is controllable. So it's a 2 by 2 system, so we're going to have 2 terms in our controllability matrix. We're going to have B and AB. We know what B is already, but we don't know what AB is, so we've got to calculate it. So let's calculate AB, and it's basically one lot of minus 8 and no lots of 16, so it's going to be minus 8 and 0. So we concatenate those horizontally. And in fact, we can already see that that is going to be a system which is full rank by inspection, because it's not got this value as 0, but we've got a 0 here and a 0 here. So that we can see by inspection is actually full rank. Let's now look at observability of the system, and we've said that the output is going to be S1, so that tells us that the output equation is going to be like this. Our C matrix is going to be 1, 0, because we want to select state 1, which is Y. Right, so C equals that. So now, again, we've got a 2 by 2 system, so we're going to have two parts in the observability matrix. We're going to have C and CA. We know what C is, but we don't know what CA is off the top of our heads, so we have to calculate that. So it's going to be rows by columns, so one lot of 0, one lot of 1, right? Concatenate, and again we can just look at that and see by inspection that's going to be rank 2, because now we've got this is already in echelon form, and there's no rows with zeros in there.